A very happy morning to all. I believe that you all stay safe and healthy. I am Robinson, Assistant Professor in the Department of Mechanical Engineering, and I am very happy in sharing a few words with all of you about our college and our department. Francis Xavier Engineering College is located at Tirunelveli city and it was established in the year 2000. FX Engineering College comes under the SCAT group of institutions. Our institution has been offered autonomous status in the year 2019. We offer 6 UG programs and 10 PG programs and research centers. The Department of Mechanical Engineering is the largest department on campus with 600 plus students, 35 faculty members, and with good infrastructure facilities. We offer BE in Mechanical Engineering and ME in Industrial Safety Engineering. The UG program is accredited by NBA, the National Board of Accreditation. We have Fanuc Center of Excellence for CNC Center, BMW and Hyundai supported mechanical labs. Our department has signed many MOU with leading manufacturing and service industries. We also offer international certificate program on CAD and NDT. Our students are actively participating in many technical competitions, winning prizes and bring laurels to our department. The research area of our faculty members are bioenergy, combustion, solar desalination, composite materials, green manufacturing, waste heat recovery, and biomass gasification. We have also organized many international conferences, workshops, and funded seminars. Today we are organizing this webinar on effect of alloying element in steel structure. I hope this session will be more useful for all of us. With this introduction, I welcome all the viewers for this session and hope we will have a productive time. Thank you.
Good evening, one and all. It gives me immense pleasure in introducing the chief guest of this evening, Dr. Don Satyaraj. He joined as assistant professor in the discipline of mechanical engineering at IIT Indore on November 2019. He did his PhD from IIT Hyderabad in the area of thermomechanical processing of high entropy alloys in the year 2016. Before joining IIT Indore, Dr. Don was worked as a postdoctoral research at TU Dresden, Germany during May 2017 to November 2019. His postdoctoral research was funded by prestigious Alexander Van Hobert Foundation. His research area of interest are micro, nano, machining of high entropy alloys, microstructure and textures evolution during basic deformation through conventional and severe plastic deformation routes, recrystallization and grain growth behavior of these advanced high entropy alloys. Thank you.
So, good evening, everyone. So, myself, Dan Satiraj. So, first of all, I'm really thankful to the organizers and management for inviting me to give a talk here. So, this is the content of my talk today. So, basically, I will start with the fundamentals of plastic deformation, and then I will go with what's the meaning of severe plastic deformation and why we have to go for severe plastic deformation. Those things I will discuss today. Then I will discuss some of the popular SPD techniques. I'm not going to cover all the techniques, so only some few SPD processes and its application I will cover, and then what is the mechanism behind about SPD processes and its microstructure evolution. Those things I will discuss today. So then in the case study, so basically I selected 3 process: ARB, HPT, and then laser short pinning. This based on the 3 process, I will give some case study by using this process. Then I will conclude my talk. Okay. So I will start with what's the plastic deformation. So maybe all of you know about it, right? It's like plastic deformation means it's a permanent distortion. It might happen due to the when you are applying the external load to the your material. Suppose, for example, here I took the tensile test. Suppose in the tensile test, you will apply a load. So up to the certain limit, you can see in the diagram there is no change in the elongation. So after reaching the yield point, clearly you can see the elongation in the sample. So it means like the tensile stress, if it exceed the yield strength of the material, the elongation will start. The similar example for compression and bending experiment. Suppose the bending stress or compressive stress, if it exceeds the yield strength of the material, that your material may bend or compress. So that is the meaning of plastic deformation. So now I'm little bit talk about what is the atomistic mechanism behind this plastic deformation. So to understand this process, you must know about the physical metallurgy. Suppose you may study means maybe you know about the dislocation and what is the defects in the crystals. Those things maybe you can understand. Maybe I will try to explain in the simple form. Maybe most of the audience are students and their background is mechanical. So suppose in atomic level, what will happen? I will try to explain by simple process. Like suppose if you take any crystalline material, you may think that the atoms are arranged in the regular fashion, right? But it's not the original. In reality, it is not the case. Actually, the crystals like has some impurities. Like impurities means it may have some foreign atoms, it may have some vacancies, or in this diagram here I showed some kind of extra plane of atom is present in the arrangement. So that will uh, make the make this plastic deformation to happen. Actually, this is the mechanism behind it. Like you may studied about edge dislocation, screw dislocation, those things. So that is the main fundamental phenomena behind this plastic deformation. So here, just I showed the edge dislocation, like how it is moving. Suppose one extra plane of atom is present here. So when you're applying the shear stress, so what will happen is like in the top side, you can see it will try to move in the right side direction. Okay, so in the bottom side, the atoms are try to move in the left side, right? So this extra plane of atom, what it will do is it will bond with the next one, then significantly that atomic movement will be transferred to the next one. So finally the deformation will happen. So similarly, there are some other mechanisms, crash slips, also claim process. By using that, the deformation will happen. So this is the basic fundamental phenomena behind the severe plastic deformation. So now I am coming to the severe plastic deformation. So what is the meaning of severe plastic deformation? So severe plastic deformation means it's nothing but it is the metal working technique. So in this case, so we are applying the very large strain on your metal or material that will undergo kind of like you are inside the material that will undergo a grain refinement. Suppose if you are starting with the coarse grain, so after the SPD process, you will end up with the ultra fine grains or nanocrystalline structure. Okay. So suppose now you may ask the question in your mind that what's the difference with the conventional process like rolling or extrusion? Also, you can deform the material. So what is the difference in this SPD process? You may think in your mind. So the answer is what is the answer here is like, suppose if I'm doing some rolling process, so that will undergo a kind of every process, the sample size thickness will reduce the start each rolling after the each pass, the sample thickness will reduce, so the cross sectional area will reduce per pass. So after certain level you can't able to roll, like up to certain level strain only you can give to the material. But in the case of SPD, basically there is no significant change in the shape of the material, shape of the metal or material. So in that point of view, you can number of passes you can do many times, so you can impart the more strain in your material. So that's what you can able to impart very high strain in this process. So normally the one measure strain value is greater than 2 means it's called it like SPD process. So that will lead to a very high dislocation density. Also, you will get some submicron grain size. So which in turn leads to the increase in the yield strength in your material. So now I'm coming to the what is the scientific history of this process. The scientific history. So mainly it start with the kind of Professor Bridgman. He is at Harvard University. He did some experiment, kind of. He did large hydrostatic pressure with concurrent shear deformation over the different samples. He tried to study the deformation of the material. For that pioneering work, he got the Nobel Prize in the year 1946 in physics. Okay, so not only this process is not only evolved in the kind of 50s 1950s. Suppose if you take our ancient history, so maybe all of you know about this sword making technique, right? So sword making, how they did is means like they will fold the kind of steel sheet, they folded many times, then they forged into kind of sword. Like the better example you can see Balian Chinese swords, wood steel from the Tipu Sultan time, and Damascus steel. This is some European sword. So you can go into this history. It is really very fascinating. Like maybe you can later on you can go into the history. It's really very fascinating story about sword making. So now, so nothing but the SPD is nothing but it is the grain refinement process. So we are trying to make the nanocrystalline, right? So there is kind of always in nanocrystalline approach, there are two approaches, top down approach and bottom up approach. In top down approach is nothing but they will refine the coarse grain into the nanocrystalline. But in the case of bottom up, like they will consolidation of the powder, then they will make it to from the bottom they will come like consolidation of powder, then they will make it to nanocrystalline. So this is the kind of powder metallurgy. Like maybe I'm not going to discuss today bottom up approach. So SPD is the top down approach. Today we are going to discuss about this process. So maybe I'm little bit I'm talking about grain refinement and nanocrystalline. So maybe some people maybe don't know what is grain, what is the nanocrystalline, what is ultra fine grain size. So for that I just show this slide here. Suppose if you take the like how the grains will look inside the crystalline material or metal. Suppose for example, if you take pomegranate fruits, it's made up of many seeds, right? Like how it's arranged inside, like that. Inside the grain, there like different grains will be arranged inside your metal. Okay, so through the SPD process, what we are trying to do is like we are trying to reduce the coarse grain into the ultra fine range. Ultra fine range or nanocrystalline range. Ultra fine means if it is less than 1 micrometer to 100 nanometer, it's called it like ultra fine grain size. If it is below 100 nanometer, it is called it like nanocrystalline grain. So what is the fundamental phenomena behind this SPDs? Already I told grain refinement. Grain refinement leads to the very smaller grain size. The typical Hall pitch relation I showed here, the usually if you are reducing the grain size, that is inversely proportional to your yield strength of your material. If you reduce the grain size, the yield strength of your material will increase. So that's why we are doing the process. So there are different type of SPD processes. So I'm not going to tell all the processes, only some of the popular technique I'm going to tell today. So so we can divide this process with respect to the material flow and deformation zone. So with respect to axial symmetry of the material flow, you can divide it into HPT and twist extrusion. With respect to without axial symmetry, equichannel angular pressing and multi-axial forcing, these are all example processes. And deformation zone into parts, for that accumulative roll bonding and repetitive corrugation and straightening process are example for this types. So now I'm coming to the most popular technique of SPD. This is the equichannel angular pressing. So as the name suggests, like the samples are equichannels, like kind of square samples or square sample or circular sample. You will push it into the two equal channels. Like in the left side I showed the some two equal channels are intersecting at one point, right? You can see here. uh, just I am inserting the your square billet from the top. So by using the plunger, so we will push the sample inside the one portion of the channel, then that will exit to your bottom of your channel, right? So mainly what is happening is the simple shear is happening in this process, like at this intersection point of this two channel. So you can see the large amount of stress and strain is developed. That is mainly due to the shear zone. Like this is the intersection point of the shear zone. At that point, it is developing a very high strain. So because of that, the fragmentation of your grains are happening. So mainly the die design is mainly based on this two angles, pi and psi. Usually they will design. So if you based on that, you will get the accumulation of strain in your material. Suppose if you are changing the angle, that will lead to the difference in the strain in the material. Suppose if I am reducing the pi angle, so what it will do is it will induce the more strain in your material. So that's what I want to say. So here, how to calculate the total strain of the material, that mathematical formulation I shown here, you can see. Okay, so now, so how they will do experiment means in ECAP process, maybe mostly they will do with some elevated temperature. Like they won't go for recrystallization temperature. Always they will keep it below the recrystallization temperature. They will heat your sample, then they will try to pass through these channels. Okay, there are like based on the process of your sample, you can differentiate the parameter. Also based on the your amount of load acting on the plunger, that also you can vary. So keep on, you can vary the parameter. You can study what kind of microstructural refinement you are getting and how it's affect the property. Those things you can study here. Just suppose if you take square sample, uh, like in the route A, what they did is they won't change the face of the sample. Like how they are inserting the sample, same way they will insert again and again for the many passes. Okay, in the route A. In the route B process, they will rotate the sample 90-degree. Okay, there are two stages in the B process. Alternatively, they will rotate 90-degree. One case they will rotate 90-degree. So in the C route, they will rotate the face 180-degree. So if you're doing like that, like you can get the different deformation zone in the material. So that inside the material, that will give some bands that will help for the fragmentation. So for typical example, here I showed the aluminum sample. Like after 4 passes, so initial sample is looks like very coarse grain. After 4 passes, you can see very ultra fine grain size, right? In the range of 1 micrometer, you can see here, right? So now I'm coming to the what is the typical application of this ECAP process. So typical application you can take, mainly if you take biomedical application, for example, you can take knee joints replacement, also dental implants. So those things and all, mainly it's made up of titanium alloy. So for example, titanium 6Al 4 vanadium is mainly used as a implant. Also for the dental implant, cobalt alloys are used. So those kind of alloys, so you need a ultra fine grain size in order to increase the higher strength. So that's why we need this kind of processes. So usually you can get the high strength structural application also. You can use the sample after your application. So all the processes has certain application, certain advantage. Also it has certain limitation. Suppose if you take ECAP, so what's the problem in ECAP is sometimes the shear zones or shear will be not distributed uniformly. That is the main drawback of the your ECAP process. Now I am coming to the accumulative roll bonding. In the accumulative roll bonding, how they will do, just I will try to explain. Like it is, they will do it in the conventional rolling machine. Suppose in the right side I showed the diagram, you can see, right? suppose you are taking some 1 mm thickness sample, right? Okay, red color and blue color I showed here. Just start from the you see the right side. Okay, uh, red color strip is 1 mm thickness and the blue color strip is 1 mm thickness. So just you are stacking that sample, then you are just rolled together inside your roller. Okay, so each pass I will give the 50% reduction. Okay, when you are stacking it is 2 mm, when you are rolling 50% means 50% reduction if you are giving means it will become 1 mm, right? This will become 1 mm. Again I will cut this uh, past sample into two halves. Again I will stack it, again I will roll it. So keep on I will do the rolling process. I won't change the sample dimension. So in that way the number of layers will increase. Also you can impart the very large plastic strain in your material. Suppose for example if you do 6 cycle you will get some 64 layers. Okay, 64 layers. So for the 64 layers, each layer thickness you can determine by using this formula. Like if you know the initial thickness and number of passes, then you can find the what is the thickness of your sample. You can find it, and also what is the accumulation of strain after the each pass also can be determined by this mathematical formulation. So what is the limitation in this method is usually for the better bonding you have to do the rolling with without lubrication. Like usually we will do the rolling, conventional rolling with lubrication, but in this case you should do without lubrication because otherwise it won't give any good bonding. So when you are doing the without lubrication, that may induce the shear over your sample surface, so that lead to the detriment to your property sometimes. So that is the limitation. So if you go for application, so mainly if you see the ARB, mainly the aluminum alloys are they did the ARB, like in the point of view of aeronautical industry, most impacted in the point of view of aluminum alloys. So aluminum alloys, why we are going for aluminum alloy? Mainly for to get the lightweight, right? So lightweight at the same time by using this process you can enhance the strength of your material. So it has direct impact on the automotive and marine industries. So those things. Okay. So now I am coming to the high pressure torsion, like the Bridgman, Professor Bridgman method I showed, right? So from that concept, they derive this HPT process. This is the first SPD process they proposed. In this process, what they will do is, like in between the two anvil, they will place the kind of disc sample. Okay, disc sample they will place it in between the two anvil. Upper anvil they will try to apply the higher pressure. Like in this method, you can apply a pressure. In the bottom anvil they will try to rotate. Because of this rotation you will get the shear in the sample, like rotation plus pressure. So those things will happen. Because of that you will get the more strain in this compared to other method. You will get very high strain in the material, but the limitation of this process is the sample size is very small, like only you can take 5 mm to 10 mm. So wherever the you can say like a very small sample application only you can use it. Like if you take strain, it is mainly depends on the number of turns of your anvil, also depends on the your thickness of the sample and radius of your sample. Like now I try to explain what is the phenomena happen during this HPT process, also in other processes also. So when you are plastically, when you are deforming the material, already I told it is the movement of the dislocation, right? So it will try to generate the more and more dislocation. Then that all the dislocation will arrange like a kind of configuration like this. B you can see the B configuration like this. It will start to arrange in the C process. In the C in the diagram of C, again the more and more dislocation will get accumulated in your sample. Also the angle of this each like you can take like each will be like kind of cell, that each cell will be the orientation will be kind of, it will become kind of highly misoriented. So finally it will become kind of subgrain. So subgrain means finally you are just reduced to the very small grain size. So similar process will happen in the other processing also. Other processing that may induce the some kind of deformation zone, same like it will increase the dislocation density. So because of that, finally you will get a submicron grain size in this material. So that's what I want to say here. So for example, in the application point of view, you can say like magnesium, people mostly tried the magnesium. Magnesium also kind of it is used for the biomedical application, also kind of corrosion application. So you can increase the mechanical property of this magnesium alloy by refining the grains, and also you can get the anisotropy, isotropic texture, like homogeneous texture. Texture means I will explain in later stage. Little bit I will explain about texture. So you will get a kind of homogeneous texture and grain refinement that will leads to the very good biocompatibility and corrosion resistance in this magnesium alloy. So people tried some of the process actually. So another some of the processes like multi-axial forging. Multi-axial forging is mainly it is derived from the your normal forging process. Here what is happening is clearly you can see that like kind of three directions, right? X, Y, Z. Like I'm changing this train path for each process. Like for example, if you take here in the left side I showed the diagram. Top side you see this is some black color, right? Black color, and one face is I showed like a green, one face I showed like a red color, right? So initially on the black side you are deforming the material, then in one direction, X direction you are deforming. Later on you will come to the red side. Okay, red side you have to deform. Okay, red side means Y direction. Okay, red side you will deform. At the third case, Z direction means green color face you will deform. So you have to continue the cycle like this, means so many cycles you can do. Okay, so by using that you can do the grain refinement. Like grain refinement, it's mainly based on the sample height, initial height, and final thickness of the process. Okay, so most of the aluminum alloys, also the titanium alloys are also tried in the multi-axial forging. So if you go for industries, so mostly they will use these processes to break down the cast texture. They will use this kind of multi-axial forging process. So okay, so next process is the repeated corrugation and straightening. This is some of the new technique. Maybe 90s they studied this process. So it's very simple actually. If you look at this, mainly it is based on the die design. In the top diagram you can see some kind of V-shaped die, right? When you are pressing it, it will bend the sample, right, in the top side. On the bottom side it is the straight tool. It will make the straightening your sample. So after straightening again, you will little bit you will move the sample again. For the next area you will apply the bending, then again it will come for straightening. It's like repeatedly you are doing the corrugation and straightening. So that's why this process is call it like repeated corrugation and straightening. Okay, so this also will leads to the significant grain refinement. Also this will leads to the very high amount of deformation zone, and shear bands will form in the material. So next I'm coming to the kind of surface modification technique. So this is kind of friction stir processing. Also it is one of the grain refinement process. So you can see most of the recent researchers are working on this friction stir processing because it's very simple to use. Like maybe all of you know about this friction stir welding process. Just you have to exchange the tool. If you exchange the tool, you can make the friction stir process. Okay, so by using the friction stir process, what we can do is like you can modify the surface. Like it is nothing but the tool is the like plunger. You can call it like a plunger or pin. That pin will go inside of your material, then it will rotate. So if you are rotating the your pin over the sample means what will happen? Like you can expect a kind of shear stress over your sample that will leads to the very significant grain refinement in the surface. So by using this friction stir process, you can generate the heterogeneous microstructure. Also, some of the research studies, how what they are doing is like suppose you want to import some metal particle inside your base metal. Suppose aluminum, silicon carbide particles, they may put over the sample. Then they will, by using this pin, they will slide over your sample. So the metal particle will go inside your base material, base metal. So that will enhance your surface property of your material. So also this friction stir processes are mainly used to change the cast structure of your material. Cast structure usually it will be coarser. In order to make the rod microstructure, they will do this FSB processing. Okay. So these are all the some of the application of this friction stir process. So now I am coming to the some of the interesting surface mechanical treatment. This also coming under the SPD, but only we are trying to modify the surface of the sample for the particular application. Okay. Suppose for example, if you want to like corrosion application, only we need a very good surface to protect the corrosion, right? No need of go inside the material, right? So for that, in order to make it, so you can use the surface modification technique. Also so this surface modification technique is mainly used to improve the fatigue life of your material. Fatigue life means like usually that will lead to the kind of voids or opening, that will cracks will initiate inside the material. Suppose by using this process, you can import the residual stress, like compressive residual stress, that will close your kind of cracks inside the material. So somewhat you can improve the fatigue life of your material, so by using this process. So first I showed the surface mechanical addition treatments. So it's called it like SMAT process. In the SMAT process, what they will do is like they will take like very small number of steel balls, they will take it. So one side of the like you can take like cylinder piston assembly. One side of the cylinder, they will fix your sample, and another side will be plunger. So they will just keep on your rotate your plunger. That will lead to give the high energy to your steel balls, right? High energy to your steel balls. So that will impact on your surface of your metal. So that will generate the kind of shock wave inside the material. So because of that, you can get the refinement. Okay, refinement, and also you will get the residual stress inside the material. So another case here I showed kind of laser shock pinning. Laser shock pinning is nothing but like they will use the kind of pulse laser beam to make the kind of high energy plasma. That high energy plasma will induce the kind of shock wave inside your material. That will lead to the kind of grain refinement. Also that will give the kind of residual compressive stress. That is really beneficial for to improve the fatigue life of your material. Okay. So that's what I want to say. So here just I showed some application of this laser shock pinning. Maybe you know, all of you know about the connecting rod, right? As a mechanical engineering student, maybe you may know the connecting rod. So in order to improve the fatigue life, so they are trying to do the sharpening over the your connecting rod. So what is the advantage in this method is like precisely you can control your laser spot. Also zero tooling cost. Also in some, suppose if you take SMAT process, I can cover the complex geometry, like if it is curvature or something it has in the part, means I can't cover in the SMAT process. But in the case of laser pinning, I can cover the even complex geometry also. Okay, that is the advantage. In the right side I showed the how the in the gear how they are doing, you can see, right? So these are all some of the example for surface modification technique. So now I am coming to the case study. I will try to show some like how to present the result. Like maybe those who are doing research, or those maybe many faculties are maybe start to thinking about the research problem. So for them it may be useful, like how to present the data, those things they can understand. So most of the work what I'm going to present here is like mainly I took from the my postdoctoral uh, professor work, also some of my PhD work, and some of my work what I'm doing in the IIT Indore. I will try to explain. Okay. So first I will try to explain how they did the ARB in the aluminum laminates. Okay. So in the aluminum laminates, mainly already I told, mostly ARB process they did for aluminum alloys in order to improve the improve the properties of the aluminum alloys. Okay. Suppose these are two grades of aluminum, 2014 6063. There are two dissimilar metals, two dissimilar aluminum alloys. It has kind of very small amount of silicon, magnesium, manganese, those things there. So 2014 is little bit hard than 6063. Okay. So they started with these two different material. Then what they did is some solution treatment they did before starting the experiment. Okay. So before starting the experiment, the microstructure looked like this. You can see the 6063 and 2014. They did some kind of three experiment. In initial stage, what they did is they took the 6063 strip. Only they are stacking to the 6063. 2014 only stacking to the 2014. And another third case, they stacked the 6063 with 2014. Okay. So they started with the very coarse grain, like 52 micrometer in rolling direction, ND direction 24 micrometer. You can see they started with coarse grain. Then after 6 ARB cycle, how the layers are look like. You can see very perfectly it's bonded, right? Like there are two dissimilar metals are very beautifully it is bonded together here. Clearly you can show, you can see here, right? So if you see the kind of microstructural point of view, like it generate the very high refinement after 6 ARB. Suppose it's in the ND direction, it's in the range of 300 micrometer. In the case of 2014, it is in the range of 0.2 micrometer. And another case, it is something like 300 nanometer grain size range. Okay, so very significant grain refinement they got it. Also, now I am introduce the term texture. Maybe you don't know about background about texture, what it means. Texture means nothing but it is the grain orientation. So usually this is also one of the parameter of the microstructure. So if you're taking grain that may sit in different crystallographic plane or and crystallographic direction. So with respect to that, you need to define your crystal orientation. Okay. So here I showed global texture means like what is the overall texture of your material, like overall. So like if you take any metal, it has millions of millions grains. Like each metal will be maybe arranged in different manner. So based on your processing, that will try to align in the particular orientation. So that will lead to the kind of characteristic texture in the metal. So that's what they showed here. Like what they showed here is like this is some kind of orientation distribution function, how they will represent the texture. In order to understand that little bit background, I will try to give here. Suppose just you assume like your crystal, like you have many grains, so that has the some orientation. So that is like a point. It is lie in this cube. Okay, in the bottom of the diagram, I showed the some cube. So here your orientation is lie together. Suppose if you are, it is 3D, in 3D space I showed. Okay, based on the Euler space I showed. If you are cutting these cubes, so you will get a 2D, right? Like suppose from the top to bottom, I am cutting with respect to 5-degree angle. Then I will get this slices. So each slices, how these orientations are located. So those things you can represent by ODF. Okay. So this top side I showed the pole figure. This is another technique to represent the texture. So with respect to poles, they will show the your crystal orientation. Okay. Now in this particular case, so what is happened in this is like there is some particular orientation is developing after 6 ARB cycle. Suppose if you see 6063 D component, this is called dilemma component. So usually that will form during the rolling process of your aluminum alloys. So same thing is happening in the ARB. Okay, dilemma component is getting increased in all of the alloys, irrespective of the alloys. So in this three different cases, so the dilemma component is increasing. Also, another one is S component. Like they try to plot the individual texture component with respect to the cycle. The S and dilemma component is increasing with respect to the your ARB cycles. Okay, so at the final end, customer, what we need to get high strength material. So you can see here, like with for the different processes, how they got the yield strength and ultimate strength. Significantly, it's increased from the 100 to 300, right? So you can see here. So from this summary of this work, I can say that so easily I can bond this different kind of aluminum alloys. Also by room temperature, I can able to go 6 cycles in ARB. Also it lead to the ultra fine grain size. Also it develops a characteristic texture. uh, Also you saw in the uh, previous slides, right? So that's what I want to say. Now I'm coming to the little bit about my work. So what I did in my PhD and during my postdoctoral work. So this is nothing but it is a kind of new alloy. So high entropy alloys. So it is a multi-component alloy. So if you take conventional alloy, for example, in previous example I showed the aluminum alloy. So the aluminum is the main base. So remaining elements are added to enhance the property of the material. But in the case of high entropy alloy, there is no base element. So all the elements will act as a principal element. Okay. So as per definition, what they are saying is it may consist of 5 or more than 5 elements that will form a very simple structures. Uh, so because of that simple structure, you can easily control the property of this material. So in that point of view, I selected this alloy. Suppose if you see the property of the alloy, some of the few HEA systems I showed here. So really very good property than conventional alloys it's giving. So fatigue toughness also very high than conventional alloys. Okay. So that mainly it's come from its core effects of these alloys. Like these are all some of the core effects. Mainly it's come from its I'm not going to tell in detail. So I will tell what I did. Okay. So what I did in my PhD is a simple thermomechanical processing of this alloy I tried to study. Okay. So what I did is I took the fine grain size material, something around 7 micrometer. The texture is very random. Here I tried to roll the material to heavy deformation. Okay. In the rolling process, I rolled. Because of the rolling, already I told the deformation will lead to the significant grain refinement. So at the end of the process, 90% reduction I got in the range of 200 nanometer. Okay. Suppose here I showed each deformation levels, how the microstructure evolve and how the texture evolves. So those things I showed here. So this is not important. What I did is after heavy deformation, I tried to anneal the sample. Okay. So in this material, I could be able to roll until 0.12 mm, like kind of very small sheet I could able to roll. After that, I can't able to roll because limitation of the your rolling process. Already I told about it, right? So after heavy deformation, I tried to anneal the material in order to get the ultra fine grain size. So I got the full recrystallization after the high temperature annealing at 700 degrees Celsius. So I got something around 1 micrometer grain size. Okay. So also this material is really it's giving very slow grain growth in this alloy. Here I try to show the some of the grain boundary characteristics. Like in the sample, you can see previous thing, like the red color lines are like these are all these red color lines. What I showed here is mainly due to the tuning, like it's like during the recrystallization many annealing twins are happening in this alloy. So that also leads to the your kind of very small grain size. Suppose in case of 700 degrees Celsius I got 800 nanometer with including twins. Okay, twins, like what I'm meaning is here is sigma 3 boundaries. So in the misorientation angle, you can see at 60-degree misorientation angle in the right side you can see the diagram. In the 60-degree you can see the peak that indicates that your sample have large number of CSL boundaries. CSL are sigma 3 boundaries. Okay, now I will try to do some tensile test, like the ultra fine grain size is giving very good ultra high strength, like 100 megapascal with appreciable ductility. Like with increasing grain size, I got the increase in ductility at the expense of your strength, right? So in this study what I got is I got the ultra fine grain size by grain refinement. Also the grain growth is very slow in this material. I understand that. Also the texture evolution is very weak, brass tape texture, like very weak texture in this alloy actually. So that's what I want to say in this in my work. Again, now I'm coming to my postdoctoral supervisor work. So they did the similar material. In the similar material they did the HPT. Maybe I forgot to tell the combustion, like this is made up of cobalt, chromium, iron, manganese, nickel. So this alloy was found by the Cantor. So mostly it is called it like Cantor alloy. So maybe if you are searching the Cantor alloy, maybe you will get this information. So it is the kind of it's a kind of FCC based crystal structure it has mainly. So in this case, so I will try to explain what they try to do. They try to refine the refine this material from the ascast structure, right? Ascast, you can see very huge, very higher grain size. After refinement, clearly you can see number of turns, right? I told with respect to increasing the number of turns, your refinement will increase, right? So with increasing the refinement, you can see the kind of deformation bands. At finally, you can see the subgrain structure, right? Subgrain structure you can see. So in this, they try to see the chemical combustion at the atomic level. So after deformation also, this 5 components are really distributed homogeneously. That's what I wanted to say here. Then again, they try to study by line profile method. They try to measure the dislocation density of the material after the HPT process. Also, they try to calculate the grain size from this calculation. So they got kind of 25 nanometer after 5 rotation. Like you can see how much they refine the material. So in my case, only I could able to do normal conventional rolling. I could able to do 200 nanometer, but in this case they could able to go until 25 nanometer. Okay, so here I showed some TM images. TM images, it's clearly it showed the very fine structure, right? 25 nanometer. Also you can see the dislocation density is increasing with number of cycles. If you go for texture, again already I told, like if you go for any process, that will lead to the characteristic texture evolution. So here mainly we are doing the shear process. So the shear related texture components will evolve in this process. So this, if you take B bar and A star, these are all shear related components. So as expected, these shear related components are increasing in this alloy, but the texture is not strong. It's really very weak. That's what I wanted to say here. Uh, Also, so we try to measure the hardness of the sample. The hardness of the sample after 5 rotation, it significantly it is increased, right? You can see here. So now, what summary I can say from this HPT process? They could able to refine until 25 nanometer. They got the very high dislocation density. Also, they understand that it has the weak brass tape texture after heavy heavy severe plastic deformation. So that's what I wanted to emphasize. Okay, so now I am coming to the important point of study. So what I did in my here in IIT Indoor, so mainly I am doing the kind of surface modification technique. So I am working with the Professor Dr. Ayer Palani in the mechatronics lab. I'm doing some experiment with the help of them. Okay, so why already I told why we have to go for laser sharp pinning, right? So in order to improve the effective life of the material, so we have to do the kind of this laser sharpening process will and like induce the residual compressive stress, which in turn give the better fatigue life to the your sample. Okay, so I will try to do in the same sample in the same canter alloy. I try to do already people studied for the ultra fine grain size. Already they studied the fatigue strength of the material, so they got a very good fatigue ratio. Like for the ultra fine range, they got 0.32 fatigue ratio they got for this material. So I wanted to see how this laser sharpening will enhance or how it will come after the processing. That's what I want to see. Maybe it's in my initial stage. I will show some of the results. Okay, so maybe you may have some doubt like what is the meaning of pinning. Like pinning means nothing but the backside of the hammer is called pin. Okay, so you are doing plastic deformation by using the pin. That's why it's called it like pinning. Okay, so in the laser sharp pinning, so what's the process happening is in the right side I showed like the like very high laser pulse will generate the plasma, high energy plasma that will induce the kind of shock wave. That shock wave refine your material. So conventional like with respect to conventional SMAT process, this laser sharpening is little bit advantage. Like even until one above 1 mm you can pin your material, but in case of mechanical sharpening it is really less actually. So that's what I want to say here. So now here like what is the what's how the LSP processes happen. So same like already I told the procedure. This is a setup we have in our lab. uh, like here we will place the sample like the NDIAC pulse laser will generate the laser pulse, so that like we will move the workpiece with respect to the like spot of interest, like where you wanted to scan your sample. We will just uh, uh, move the sample, then that will pin your sample. Okay, so now for this study what I took is basically I took kind of two different condition I took in this alloy. Okay, so maybe I will try to explain. Maybe if your background is material science, maybe you can understand. Okay, so this is the starting material. Okay, 20 micrometer grain size. I took this material as a starting material, then I rolled to 97 percentage, something around 0.3 mm I got. Okay, then I anneal the sample at different two temperatures. Okay, 650 degree and 800 degree Celsius. Why I did two different temperatures, I will try to explain. Because in this character alloy, so what they told is below 700 if you are heat treating the sample, that will form some chromium rich precipitate. Okay, so you can in the left side microstructure clearly you can see the precipitation like little bit sigma phase you can see here, right? I left side I showed. In the right side here you can see the misorientation angle distribution. Based on that I got the grain size in the range of 550 nanometer in this process with precipitation. Precipitation also will increase the strength of your material. So that is my idea. So that's why I purposefully induce the precipitation in the metal. So in another case I annealed at heat treated at 800 degrees Celsius. So there I don't have any precipitation. Also the grain size little bit, it is bigger size, 1 micrometer grain size. I took this one also ultra fine grain size. So two different grain sizes I took. Then I did the pinning. Okay, so pinning normally you can put the directly you can pin over the sample, or you can put inside your water, like inside the water you can place the sample. If you're placing the inside the water, so what is the advantage is like it won't affect the surface much. This plasma, the high energy plasma, most of the time that will melt your little bit, vaporize your surface. That won't happen when you're using the water. So I did it in the water. So after sharpening, my grain is refined to something around 345 nanometer. You can clearly you can see here. After 800 sample is refined to something around 600 nanometer. It's refined. In XRD process, you can see that like precipitation, you can see sigma phase, you can see here. Also, majority of the peaks are belongs to FCC. Okay. After sharpening, in the red color, peaks are little bit moved towards the right. So it means it tells that your sample already have some residual stress. So that's what I want to say here. Um, like in order to measure the residual stress analysis, there are so many methods are there. One sine square method, sine square psi method is one of the accepted method. So by using this method, you can measure your residual stress in your sample. Okay. Next, what is the characterization I did? I showed. I tried to show here. Like suppose if you take surface roughness, I try to see each condition, because like after the processing, always the surface roughness is very very important, right? So I try to see the surface roughness. So by using the water medium, that has the very less surface roughness, 0.047. It's not at all affected the surface. That's why I choose the water medium. Suppose without water medium, how the surface affected, that you can see it in the right side diagram. 3D profile I showed how rough you can see the sample. Okay. So micro hardness, after the LSP process, you can see that near the surface there is an increment in the hardness, but if you go inside the material, there is no significant enhancement. As a tensile test, I could able to see after LSP there is a significant enhancement in the strength. Also the ductility also, it's not affected in case of 800-degree sample, but in case of 650, the strength is really high, but ductility is little bit reduced, like after 13% I got after LSP. Okay. So based on this study, you can understand that from the XRD graph, you can understand that how compressive residual stress, also how to measure the surface roughness measurement, those things you may understand. From the EBST analysis, like you can say that the formation of low angle boundaries, you can directly you can correlate with the higher dislocation density in the material. Okay. So finally, the ultra fine grain size in this HEA is giving very good property. That's what I want to conclude today. So overall summary. So maybe as a student, maybe you people can understand what is the severe plastic deformation, how the grain refinement is happening at some of the processes. So which in turn that will lead to the improvement in the structural or functional property of your material. Okay. So for the researchers, or maybe those who are new faculties, they want to do some PhD in the area, they may get the idea about what kind of research is going in this SPD. Also how to present the data and interpretation, how to do, maybe little bit I showed some through the case study. Okay. So finally, the microstructure processing performance of material may be appreciated. Okay. So this is some of the information I want to show. This is some of the nano SPD conference. So every year that will happen. So this year it is happening in IAC Bangalore. Okay. So conference chairman is Professor Satyam Suhas. So here you can find those who are working in this SPD processes, like those who are in India National Organizing Committee. You can see many professors working in SPD processes. You can see also in international committee also you can see some of the professors. So just you for the students, you can aim for your PhD to these professors. Like they are all very pioneer in this field. So every maybe this nano SPD conference now they may be postponed to the next year because of this COVID issue. Okay, so now I will try to acknowledge my PhD supervisor and my postdoc supervisor, Professor Varner Stokesy from TU Dresden, also Professor Suhas from IIS Bangalore, and Dr. Satish Kumar from DMRL, and Professor Palani from our lab, IIT Indore, and also Professor A from Taiwan, also Alexander Wan Humboldt Fellowship for my financial support. For that, I want to thank the AVH Foundation. So finally, here just a little bit advertisement for me. Just I showed the what are all my research areas, like what I want to do it here in IIT Indore. So like I put it the surface modification technique. Also, I would like to do micro nano machining of this high entropy alloys for in the coming years. Maybe those who are interested in PhD may apply in the next semester. Okay. So thank you very much for your kind attention towards this talk. So, okay, I will conclude with this. Maybe we will conclude the talk. Maybe if you have any question, maybe I can carry on. Okay, thank you very much.
Thank you, sir. There are a few questions from the participants.
Yeah, you can ask.
First question, what do you mean by recrystallization temperature and
Okay.
whether it will vary from material to material?
Yeah, definitely. So recrystallization means nothing but it is like when, like already I told, like thermomechanical processing means usually you will do the plastic deformation. So during the plastic deformation, it will induce the more dislocation. So after that, you will try to form the new grains. Okay, like dislocation free grains. So if it is your sample is when it will form this dislocation free grains means you have to heat at high temperature. Like material to material, it will differ. Okay, usually the strain free grains are the formation of strain free grains are usually call it like recrystallization. That will vary material to material. Uh, uh, that's what I want to say here. Okay. What's the next
Thank
question?
you, sir. Thank you, sir. Next question. Can we apply or whether it is applicable SPT technique for
Yes,
polymer-based
definitely.
materials?
Like people are trying for polymer material, metal matrix composites, all the processes, like all the kind of material people are doing research. Like you can see the literatures, like already there many. You can do the refinement actually. Yeah,
Thank you, sir.
yeah,
Next question.
yeah.
In few research papers,
Yeah.
ASTM D638 is used for tensile testing. In some other papers, ASTM D3039 for polymer matrix composite. Which
Okay.
one is preferable, sir?
No. You can do at any standard. Like it's your wish. Like whatever method you are following, you should mention in your journal. Okay. So these two methods also you can follow, but you should write in your manuscript. So that is very important. That's it.
Thank you, sir. Next question.
Yeah.
What is the usage of severe plastic deformation process in biomaterials?
Already I showed some example, right? Like biomedical implants, like knee joint replacement. Also I showed some dental implants like the titanium alloys or cobalt based alloys. This and all already it is in the usage. Okay, so maybe you can study about ultra fine grains of titanium alloys. uh, they are using it, this process. So it is really developed process for a biomedical application actually. Yeah.
Uh,
Is
Thank
there
you,
any
sir.
question? Yeah.
Last question, sir.
Yeah.
Can thermoplastic material can be used for deformation?
Yeah, you can use any, see, you can use the any material for the deformation. So final thing, what will happen is you have to get some, if you want some refinement, you can use it. Suppose if it is the brittle material, that may, when you are applying the stress, that may sometimes that may broke, so you can't do some refinement to enhance the strength. Okay, so that is my answer for
Uh,
this
thank,
question. Yeah,
thank you, sir. Thank you very much.
yeah, okay, okay, really I think it's, I think something useful session for the students, I think maybe we can conclude. Yeah, yeah, thank you.
Good evening, everyone. I am honored to have this opportunity to give you a vote of thanks on this special day. I hope you all enjoyed this session. I liked Dr. Dan Satiraj sir's speech. The content he delivered here was very informative, and the way the sir was explained, extraordinary. Thank you, sir. We are very thankful to our management, our beloved principal, Dr. V. Murugan sir. My sincere thanks to the head of the department, Dr. Joe Patrick sir, Professor J.Y. Arthur Jabraj, Professor Robinson sir, and all my student colleagues and student volunteers for their support. This webinar was made successful only because of the well-wishers, followers, and the participants of this event. On behalf of our institution and management, I sincerely extend our heartfelt thanks to all for making this event success. With this kind message, we move to the end of this today's seminar. Thank you all.